So in this video, we're going to look at the idea behind what's called unit vectors. And we're going to see how these relate to the work that we're going to do and how we can actually use them to describe vectors themselves and break them down into component parts. Now, the first thing we need to remember is what we exactly mean when we say unit vectors. Now, a unit vector, quite simply, is a vector whose magnitude is 1, i.e. the size of the vector is 1. So if I give you this vector here, u, of these components, 1/3, 2/3, and -2/3, and I wanted to calculate the magnitude of u, I'd still follow the exact same formula as before. So I'd do the square of each of them, so 1/3 squared, plus the 2/3 squared, plus the -2/3 squared. I'd then square them, add them, take the square root. So I'd then have the square root, well 1/3 squared is a 1/9, plus 2/3 squared is 4/9, and then -2/3 squared is another 4/9. So 1/9 plus 4/9 plus 4/9 again gives me the square root of 1, which is just 1. So the magnitude of that vector there is 1, which means it is a unit vector. Now, unit vectors allow me to look at a fundamental part of vectors, and that's what we call direction vectors. Now, if we look at any system with x, y, and z, what we are able to do is describe each direction with a unit vector which points in that direction. So if we look at the x-axis, I can describe a unit vector I pointing in that direction with a magnitude of 1. If I look in the y direction, I've got a unit vector pointing in that direction, which we call j. And if I look in the z direction, I've got a unit vector pointing that way, which we call k. Now, each of these vectors is given by these vector component parts. So I is given by 1, 0, 0, j is given by 0, 1, 0, and k is given by 0, 0, 1. Now, the point of these three vectors is I can write any journey to a point, so any vector within our system, as a combination of these, as a combination of products of these put together depending on what my travel in that direction is. So let me show you exactly what I mean. Imagine I want to take this vector A and express it in that term. Now, as I've said, every vector can be expressed in terms of this I, j, and k. Now, the I, j, and k are called base vectors. So this one here can be expressed in terms of these. Now, remember what these vectors are. I was given by 1, 0, 0. It's in the x direction. J was given by 0, 1, 0, the y direction, and k was given by 0, 0, 1 in the z direction. I can break this down using these to then represent it in terms of this. Well, what this one here is, I can remember that it's 5, 0, 0, so just my vector in the x direction, plus my vector in the y direction, 0, -2, 0, plus my vector in the z direction, 0, 0, 7. Now, each of these can then be written as a product of these. So 5, 0, 0 is the equivalent of 5 times the 1, 0, 0 vector. It's then -2, because the -2 here, so if I multiply this whole thing by -2, I get it, times the 0, 1, 0 vector. Then plus 7 times the 0, 0, 1 vector. Now, each of these can be written as one of these. So this vector A, which is 5, -2, 7, can be written as 5i, take away 2j, plus 7k. Any vector in our system can be written in this format. The easy way to look at it is the I is your x, the j is your y, and the z is your k. They tell you about the direction and the movement in each of those directions. We can also take a vector that's written like this and put it back into column vector form. So this one here, 6i minus 2k, well, that's 6 times the I vector, which is the 1, 0, 0. Now, our j vector represents the y direction, the 0, 1, 0, but there's none of that, so there's no j. So that's technically the same as writing plus 0 times 1 times 0, 1, 0. Then minus 2 times the k vector, which is 0, 0, 1. I can then use vector multiplication to give me these vectors. So that's going to be the equivalent of 6, 0, 0 for that direction, plus, well, this vector is just 0, 0, 0. Everything multiplied by 0 in there just disappears. It's then plus the 0, 0, or -2. Now a key thing I'm going to point out here before I do anything else, I've made this a plus. I take the entire part of the -2 in when I do the calculation. We always want a plus written out here, so it's each of the three components added together. We always take the sign in with us in order to be able to do that. Because what this now allows me to do is combine all three of these, and I can write it as 6, 0, -2. So I've written my column vector B as a column vector there, rather than having it in terms of my base vectors I, j, and k there. We're able to interchange between these two. This is a fundamental thing when we are doing vectors. We have to be able to write it in terms of these direction vectors. It's quite important to be able to do. What we also have to be able to do using these direction vectors and the base vectors is write any vector within our system as a unit vector which is parallel in direction to the original. So you could imagine I've got a vector going this way. Let's say it's the vector A. Now this vector could have a set magnitude. Let's say it's 10, 11, 12, whatever. There it is there. I am able to somehow calculate a vector that is parallel to that, but is a unit vector. So the magnitude of that vector is equal to 1. And it's pointing the same direction as that one. What I'm then able to do is use this to calculate any vector along the pathway of A. Now when we're doing this, there's two steps we have to follow. The first thing we have to do is find the magnitude of the vector we want. So find the magnitude of our vector A. We then divide every component part of A by the magnitude. Now I'll show you exactly what I mean when I'm saying that just now. Imagine I've got a vector A here which is 4, -4, 2. And I want to find the unit vector parallel to this. Step 1, we have to find the magnitude of A. So we start by doing the magnitude of A equals and then follow our set steps for that. So 4 squared plus -4 squared plus 2 squared. So that's then given by the square root of 16 plus 16 plus 4, which is the square root of 16 plus 16 is 32. 32 plus 4 is 36. Square root of 36 is just 6. So the magnitude of my vector is equal to 6. What we then want is to get the unit vector parallel to this. So what that then means is I could take my vector A and divide every component part in it by this, i.e. I can take my vector A and do 1/6 of it, times the whole thing by 1 over the magnitude. So it's going to be 1/6 of 4, -4, and 2. And when I take this in, I end up getting 4 over 6, -4 over 6, and 2 over 6. Is my three components. Now each of these components can be simplified. You always simplify as much as you can. That gives me the vector A being 4 over 6 is just 2/3, then it's -2/3, and then 2 over 6 is just 1/3 there. So I've now got a unit vector pointing in the direction of A, and I can use this to get any vector along that pathway that A is pointing. I can get any vector along that pathway using this vector here. It's quite a fundamental thing that we have to be able to do. Unit vectors are vital, as are the base components, i.e. the I, j, k. We have to be able to work with them quite openly and explicitly when we're calculating any vector and when we're being able to write any vector out.